Hello friends, welcome to fluid mechanics classes. So before lockdown we had discussed two modules, that is module number 1 basics, introduction to fluid mechanics, and module number 2 fluid kinematics. Okay. Now we are going to discuss module number 3, that is fluid dynamics. So before going to module number 3, so let us brush up few concepts regarding fluid kinematics, because to understand fluid dynamics we need few definitions from fluid kinematics, which will help us in understanding the concepts of dynamics in a better way. Okay, so first I'll quickly brush up the concepts of module number 2. Once we complete this, in my next session I'll start with the fluid dynamics. Okay, so module number 2 consists of fluid kinematics. So what is fluid kinematics? That I'll take up later. So the topics that we are going to cover in this is methods of describing fluid motion and the types of fluid flow. Next topic is continuity equation, and after that velocity and acceleration of fluid particles, and the last topic is flow patterns and flow visualization. So in this we'll be studying various definitions and the expressions for that. Okay, so the terms that we are going to study here is streamlines, streak lines, path lines. What is the meaning of that, and what is the mathematical expression of these terms, and we'll also be studying velocity potential function, which is denoted by symbol pi, and stream function, the symbol for stream function is psi. So to start with, what is kinematics? So it is the branch of science which deals with the motion of particles without considering the forces causing the motion. Means we are going to study the motion of fluid particles, but we are not going to consider the forces that are causing the motion. We are going to just study the behavior of fluid particles. We are not going to consider the forces that caused that fluid particles to move. So when we are studying the kinematics, the motion of fluid particles, so basically we describe in two methods. So first one is Lagrangian method and second one is Eulerian method. So already these topics we already covered this in the classes. I'm just going to give you some information so that you can recall the concepts and you can answer the assignment questions smoothly. So first of all, what is the Lagrangian method? Lagrangian method means, so in our lower classes we have been studying this method of approach. Like if you consider Newton's law, wherein we are going to consider a particular particle, and as it moves we are going to study the behavior of that particle. Okay, so I have given the examples. When you are playing the carom, so your concentration is only on one puck, so you are not worried about other particles. So your concentration is only on one particle and you are going to study only that particle. That type of approach we call it as Lagrangian approach. So the second one is Eulerian method or Eulerian approach. Eulerian approach, it says, so here we are not going to study individual particles. Instead of that, we in space we define a finite volume, we call it as flow domain or control volume. Okay, so whichever particles enters that a control volume or flow domain. So we study those particles, those we call it as field variables. So it can be velocity, it can be acceleration. So whatever particle enters that control volume, we are going to study that. So that is the main difference between Lagrangian approach and Eulerian approach. So here the field, the properties, we call them as field variables. So these field variables, they are function of space and time. So in my discussion I am going to consider a Cartesian coordinate system for better understanding, and we are more familiar with this approach of Cartesian system. Okay, so suppose if you take velocity or pressure or acceleration, okay, so they depend on space. So space, x, y, z coordinates, and time. So that's why whenever if I write acceleration, okay, I specify the reference with respect to space and time. Okay, so the next topic that we discussed was types of fluid flow. Okay, here mainly we have 6 types of fluid flow that I have mentioned, and we have discussed this in the class. The first one is steady and unsteady flow. What do you mean by steady flow, unsteady flow? So steady flow means with respect to space, with respect to time, the field variables are constant. Steady flow is defined as type of flow in which the fluid characteristics like velocity, pressure, density, okay, at a point do not change with time. Means I told you to remember, steady means with respect to time, uniform means with respect to space. Okay, so I think you people can recall these techniques, how to recall this. So steady means with respect to time, if any property is constant, we call it as steady variable, or if it is not constant with respect to time, then we call it as unsteady. Similar way, uniform and non-uniform flow. Uniform means with respect to space, it doesn't change, the property will not change with respect to space, then we call it as uniform flow. If it changes, then we call it as non-uniform flow. Next one is laminar and a turbulent flow. So laminar means what? It is an organized flow, it is non-intermixing, there is no intermixing of the fluid as it flows, and we get laminar flow in low velocity. Whereas the turbulent flow is, it is a disorganized flow, and there is intermixing, as you can see from the sketch. In laminar flow, the fluid will be moving in a very disciplined manner, parallel to each other, one behind the other, whereas in turbulent flow, it's not organized. Okay, so we call it as a turbulent. The next term is a compressible and incompressible flow. So compressible flow means the density of the fluid, if it is not a constant, then we call it as compressible flow. Okay, incompressible means the density is constant. So all the liquids, we consider them as incompressible flow, so the density is constant, whereas the gas, we consider them as compressible flow. The next term is rotational and irrotational flow. So rotational means the fluid particles, when it is flowing, so it is also rotating along its axis. As you can see from the sketch, the fluid particle is flowing, but as it flows, it also rotates along its axis. So this kind of flow, we call it as rotational flow. So if it doesn't rotate along its axis, then we call it as irrotational. The next term is 1, 2 and 3 dimensional flow. So as the name says, one dimensional means the flow parameters such as velocity is function of time and one space coordinate only. So velocity along x-axis I denote it by u, along y-axis we denote it by v, and along z-axis we denote the component of velocity by w. So I have written here u, v, w are velocity components in x, y and z direction respectively. So one dimensional flow means we are not going to consider the component of velocity along y and z direction. We are going to consider the component of velocity in only x direction. So it can be either x direction or it can be either y direction or z direction. Means we are going to consider only one axis, only one direction. That is called as one dimension. Two dimension means we are going to consider two axes, whereas the third axis we are not going to consider it. And three dimensional flow means wherein we are going to consider all the three directions. And if I take the example of velocity, okay, so along x direction it is u, which is function of space coordinates x, y, z, and v, the component of velocity along y direction, it's also function of x, y, z, and component of velocity along z direction is also function of x, y, z. Means three dimension means we are going to consider all the three coordinate systems. The next important term that we need to understand is rate of flow or discharge. So what is rate of flow or discharge? It is defined as quantity of fluid flowing per second through a section of pipe or channel. So already you know the definition of discharge, but I would like to give more details with respect to fluids and gases. We need to know the units for that. So if you are considering the fluid, then the unit of discharge is meter cube per second or liters per second. If you are considering the gas, then the discharge is expressed as weight of fluid flowing across the section per second, and the unit is newtons per second or kg of per second. And we are denoting discharge with symbol Q, which is equal to the cross section area A and velocity of fluid across the cross section. Next topic, and very important topic, is the continuity equation. So continuity equation, directly I will go to the formula of that. So continuity equation is rho a v is constant. So continuity equation is nothing but its conservation of mass. So whatever mass that enters a control volume, the same amount of mass has to leave the control volume if there is no storage, or whatever mass enters into control volume, if some of the mass is stored here, then the difference of mass has to come out of the control volume. Okay, so it's nothing but conservation of mass principle. So for a fluid flowing through a pipe at all the cross sections, the quantity of fluid per second is constant. Okay, so whatever I have explained, it is very simple one. If the fluid is incompressible, then the rho terms, density terms are equal, so we get A1 V1 is equal to A2 V2. Okay, this is a very simple expression for continuity equation, but the most important is continuity equation in three dimensions. Suppose if I take a three dimension x, y and z direction, and the component of velocity along x direction as u, along y direction as v, and along z direction as w, then the expression for the continuity equation in 3 dimension is looks something like this. So I'm not going to explain in detail regarding the derivations. So already you have the notes for this, so you can go through. Okay, here I'm just going to explain the important concepts, okay, so that we can recall whatever we have discussed in the class. So the expression for the continuity equation in 3 dimension is this, the expression in the box. So dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z plus dou rho by dou t is equal to. So whenever, if you consider steady flow, steady means what? With respect to time, the property is constant. So here if you look at the expression, the first 3 terms, they are with respect to space, whereas the fourth term, if you look at the denominator, it is with respect to time. So steady flow means, so whatever properties that are function of time, they will be constant, means cancelled out. So dou rho by dou t is 0. So for a steady flow, continuity equation is this. We take only 3 terms which are with respect to space. Okay. Suppose if I take the next case, if the fluid, if it is incompressible, then the density is constant. Okay. So in this expression we have rho in the numerator. So if I consider incompressible flow, then this rho terms becomes constant, so I can take this out. So the rho get cancels, so the expression that remains is dou u by dou x plus dou v by dou y plus dou w by dou z. Okay, so you have to remember this general expression. If we can remember the general expression, so based on the conditions we can modify this expression. And the continuity equation is very important from the examination point of view. Okay, so very important note here is, whenever fluid flow takes place, continuity equation has to be satisfied. This is very important, you have to remember this. So even in the problems they'll ask question whether the fluid flow is possible or not. If the question is asked like, they'll give you some mathematical expressions, some relations, and they will ask you whether the fluid flow is possible or not. Okay, so what we have to do, we have to check for a continuity equation. If the given expression, given problem, if it satisfies the continuity equation, then fluid flow is possible. Very important. Already in the class I have solved few examples regarding this. You can just go back and check the problems. I'll just repeat once again. Whenever fluid flow takes place, a continuity equation has to be satisfied. Very important. Okay, the next important topic is velocity and acceleration. Okay, so in this topic, velocity and acceleration, we consider v as resultant velocity at any point in fluid flow, and its component along x, y and z direction, we take it as uv w. Okay, and this uv it is function of space coordinates and time, as we discussed in the beginning. All the properties we are going, so whatever we are discussing, it is all with respect to Eulerian approach. So in Eulerian approach, we consider the control volume, and whatever flow fields or properties, they are function of space coordinate and time. Okay, so for example, if you take velocity u, the component of component u, so it is function of space coordinates x, y, z and t, similarly v and w. So the resultant velocity v is equal to u plus v plus w. This I have written this in vector form. This I, j, k, they refer to unit vectors. Okay, and the magnitude of this velocity is square root of u square plus v square plus k square. So this is all vectors which you people have studied in your lower classes. Okay, so next one is acceleration. So we denote acceleration with symbol a, and along the x direction, y direction and z direction we denote by ax, ay, az, and this I have written in vector form, and the resultant of that is square root of ax square, ay square and az square. Okay, now here very important is the acceleration along x direction. Okay, if you go by chain rule, okay, ax is du by dt, and if you apply the chain rule and if you simplify this, then the acceleration along the x direction you get it as u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. And similarly, if you apply the chain rule for the component of acceleration along y direction, you will get this expression, and for z direction you get this expression. Okay, so in the class we have I have given you the logic to remember. There is no substitute, you just have to write and practice and remember. Okay, so you remember expression for 1. Based on this you can remember the expression for ay and az. Okay, it's very simple. Okay, so if you are considering on a x direction, so you have to use u all this side. If you are considering along y direction, v here, and if you are considering z direction, w here. So u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. And similarly ay is equal to u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. Similarly az. Okay, so here one important thing that you have to remember is we get two sets. Okay, so ax is equal to, we get expression with respect to space, and there is one expression with respect to time. Okay, so this expression which is with respect to space coordinate, we call it as a convective acceleration. Okay, and dou u by dou t, okay, acceleration with respect to time, this we call it as local or temporal acceleration. Okay, so what is convective acceleration? It is defined as the rate of change of velocity due to the change of position of fluid particles in a fluid flow. Okay, so acceleration, okay, rate of change of velocity with respect to position, okay, we call it as convective acceleration. Okay, if it is with respect to time, then we call it as local acceleration. Okay, so even in the class I had given you a tabular column. Okay, whereas this is steady and uniform flow. What is the expression for convective acceleration? So for steady flow, okay, and uniform flow, steady flow means with respect to time it is constant. So temporal or local acceleration is with respect to time. So with respect to time it is constant. Uniform means with respect to space constant. So it is 0, 0. Whereas steady flow means steady and non-uniform flow. Second case, steady and non-uniform flow. Okay, steady flow means with respect to time it is constant. So local or temporal acceleration 0, and non-uniform means, okay, so the expression for convective acceleration exists. Okay, then we get some expression for that. And unsteady and uniform. Unsteady means with respect to time, okay, which is not constant, so we get some expression here, whereas for uniform it is 0. So when it is unsteady and non-uniform, both convective acceleration and local acceleration exists, okay. And after this we had discussed few examples. I had taken up few examples, and we also discussed some of the questions that had appeared in the competitive examinations, okay. So you can just go through them, okay. So the next topic is, and the last topic in this module is, flow patterns and flow visualizations. So I'm not going to explain you all the details, you can just go through the notes. So I'll take up the terms, okay. So streamlines, streak lines and path lines. So these are very important terms. So when you are doing the analysis, like as an engineer, when you use some mathematical formulas and you get lot of data, so when I look at those numbers, it is difficult for the human being to picturize that, okay. So to understand how the flow is taking place just looking at the numbers. So in those times, in those difficult situations, so these flow visualization techniques will help us understanding the flow. So as the saying goes, a picture is worth 1,000 words. So whatever calculations, whatever results we have got, if we can convert all those numbers into some graph or with some flow visualization, okay, then it is easy for us to understand. With respect to that, we need to know few terms, okay. So those are streamlines, streak lines, path lines, stream tubes, and what is velocity function, stream function, what is the relation for that. So if these are important in understanding of the flow visualization techniques, okay. So first let us go to streamlines. So what is a streamline? Streamline is a curve. Streamline is a curve that is everywhere tangent to the instantaneous local velocity vector, okay. So streamline means if I take one particle and if I draw the tangent to that curve, means the particle as it flows, if I draw the tangent, okay, then it indicates the velocity of that particle along that direction, okay. So streamlines cannot be directly observed experimentally except in steady flow fields, okay, in which they are coincident with path lines and streak lines that we'll see later, okay. The expression for streamline is dy by dx is equal to v by u. So you can just go through the content of this, okay, which we have discussed in the class. I'm just giving you the main important topics, and the bundle of streamlines we call them as stream tubes, okay. So the next one is path line. So what is a path line? A path line is the actual path traveled by an individual fluid particle over some time period. So you have just observed one fluid particle, and if you keep observing as it moves, then the path traveled by that fluid particle we call it as path line, okay. And streak line is locus of fluid particles that have passed sequentially through a prescribed point in the flow. So for example, if I take a point P, and if there are if I take 4 fluid particles that have passed through this point P, and the locus of all these 4 particles, we call it as streak line. So you can see I have connected the line from 4 to 3, 3 to 2, 2 to 1, and 1 to P. So this line we call it as streak line, the locus of the particles, okay, so that have passed through a point, okay. And if I take the individual particle, the path that it has traveled, then we call it as path line. So understand the difference, streak line and path line, okay. The next topic that we discussed in the class was velocity potential function and stream function, okay. So velocity potential function, we denote it by symbol phi. So it is defined as scalar function of space and time such that its negative derivative with respect to any direction gives the fluid velocity in that direction. Means suppose if I take x direction, okay, so I have some expression, okay, expression for pi, some mathematical expression. So if I differentiate that mathematical expression, that which we denoted by symbol pi, with respect to that direction, suppose if I take x direction, okay, if I differentiate this pi with respect to x direction, then I will get the velocity component along that direction. So if I differentiate that pi along the y direction, okay, then I'll get velocity component along y direction, that is v. If I differentiate that pi along the z direction, so I'll get the velocity component along z direction, w, okay. So we have solved examples on this in the class, so you can just go through my notes, okay, so you will understand it better. And the next one is stream function, okay. So stream function, so it is also a mathematical expression, stream function. So instead of writing du by dx plus dv by dy, so we are going to replace these terms, okay, which will be difficult for us to analyze, okay. We are going to replace these kinds of combination of terms with a single term called as psi, and this psi we call it as stream function, okay. So if I differentiate stream function with respect to any direction, I will get the component of velocity, okay, at right angles to that direction. So we define stream function, okay, we for 2 dimensions, okay. So we don't consider stream function for 3 dimension, okay. So if I differentiate stream function along x direction, then I will get the velocity component at right angles to that, that is v, okay. If I differentiate stream function along y direction, then I will get the velocity component along x direction. So this is about stream function. So we have discussed in detail about all these topics in the class, okay. So before going to the next module, I just thought of recalling all these concepts, since there is gap of almost 3 weeks, okay. So I hope that you people have understood this. So also I'm going to give you few assignment questions, objective type, so you can answer them, okay. So I'll give you some time for the preparation and going through all these notes. You can prepare, okay, and answer the assignment questions. Thank you.